need somebody to make me
real.
We need some real power.
Yeah, well, but he's just signing in.
Right.
So how's things going? It's morning, right? Somewhere it's morning, somewhere it's very early morning. I'm not sure anybody from the Pacific time zone is listening in. I doubt.
Well,
I'm sorry, I was in the wrong room. So,
yeah, there used to be
Hi,
this,
Misha. How's it going?
there used to be this pedagogical series that you can learn in your sleep. So maybe they are plugged in like that.
Marco, do you need to share your screen? So I gave permission.
Yeah, I need, yes, I need to share screen, yes.
Yeah, so you can do it now.
Oh, okay, just a second. Screen. One. Okay. Uh-huh, all right. Okay.
Yeah, let's probably wait a couple of minutes for more people.
Yeah.
Yeah, just usual warning. So you are recorded for kind of.
I see. Okay. Wait. There's nothing embarrassing in the background.
Not yet. Another request. Can you send me your slides afterwards? So just.
Should I do it immediately, or I can do, because maybe I will write. Yeah. Okay.
No rush. I just post it online later for kind of.
All right. Oh, I see also Volodya's here.
Yes, yes, everyone is here. Tout le monde.
Yes.
Yeah. Volodya changed voice.
Me? Yeah.
Well,
You are kidding.
ask for Volodya and Loni replied. Sorry.
You are kidding. No.
So you see, I'm also making some advertisement for a different institute now.
For what? Sorry.
It's the wrong institute, but I'm making an advertisement for them.
Mm-hmm.
It's the Korean one.
Oh.
Product placement is called. That's what.
Oh, by the way, I apologize. I listed only SISSA in this announcement. I kind of was lazy to mention all you in other places where you work.
Yeah, well, it's okay. It's no problem. I see.
Okay, 15 seconds more from people for West Coast. Yeah, by the way, Georgi, congratulations.
Thank you.
Congratulations with your new job.
Thank you very much. News gets around fast, I can see.
So who's got the new job?
Yergi, Lamandon.
Okay. Congratulations.
Okay, should we start? Marco.
Well, I'm ready.
We are happy to have Marco Bertola today, who will speak about extended Goldman symplectic structure in Fock-Goncharov coordinates. Please, Mark.
Thank you very much for the invitation. It's always nice to visit Michigan.
Yeah.
And,
no beers this time.
Excuse me?
No beers this time.
No beers. Yeah. Okay. So as you can see, it's from my couch to yours. Just a second. Let me orient this in a better way. Okay. Now it's got, okay. So what we want to do is to explain how these Fock-Goncharov coordinates, which of course I will define in due term. Just a second, how can I mute? Unmutable, just a second.
No, you can turn off sound in one device, kind of.
Yeah, exactly. I'm trying to do that, but it refuses to. Okay, maybe now I got it. Can you still hear me?
Yeah.
Okay, excellent. Right, so I will recall what is Fock-Goncharov coordinate, and of course what is the Goldman structure and everything. But main message is that we are trying to find log canonical coordinates for the Goldman bracket. So let's start with a setup. I have a Riemann surface of genus G, so I'm going to draw the standard picture, right? Here's my Riemann surface, this is genus 2, and a certain number of punctures. So what in our situation, the genus has just to be bigger or equal than 0, and some number of punctures. The puncture I think we can draw in red. And then I want to describe the character variety, which is just the space of homomorphism from the fundamental group of this punctured Riemann surface with values in some Lie group G, quotients with respect to the group G. In practice, I will use SLNC, but as you will see, some formulas become very easily generalizable to an arbitrary Lie group. So how do we think of this object? We can think of this object as follows. You take a base point on the Riemann surface, and then you draw the generators for the fundamental group with base point P0. And typically we can draw them like this. This is one, let's call it A1. Then there will be another one. Now I don't know exactly. I may get the orientation wrong, but B1, then A2, and B2. So those are the standard generators of the fundamental group. Maybe make it less cluttered. And then we have, let's make just 2 punctures here. And then we have some loops based at P0, which are contractible to the punctures. Gamma 1, gamma n. And in these, now I'm not sure I draw them in this correct order, but they satisfy in the fundamental group just one relation, which is that gamma, well, it's written here, but gamma 1, gamma n composed with the commutator of the cycle generating the A and B. So let's call them alpha J, beta J inverse, alpha J inverse, beta J, products from 1 to G, is the identity in pi 1. So convenient way of thinking of a representation of this group is to just produce a collection of 2G plus n matrices which satisfy the same formal relation, and that's what I'm doing here. So I'm choosing some matrices MJ that represents the monodromy. What we call the monodromy around this contractible loop to the punctures, and then AJs and BJs, a total of 2G plus n matrices, such that the corresponding product mimics exactly this relation in the fundamental group. We are not just considering this collection as a collection of matrices, but as a quotient space. We are taking the quotient, where the quotient is just conjugation by simultaneous diagonal, simultaneous conjugation action by the group G SLN, where of course this G is an arbitrary matrix in SLN. Let's see. Okay, and this is what we call the character variety. If I want the monodromy associated to an arbitrary loop, let's call it gamma, what we have to do is simply to express this gamma as a word in the letters gamma J inverse, alpha J, beta J, and alpha J inverse, beta J inverse. And then the corresponding matrix M gamma is the same, right? I guess you understand what I mean. It's the same word with the letters represented by matrices. All right, so it's a very practical, direct approach and way of thinking of the character variety. Now, the character variety as a global object is a relatively singular, complicated object, but we are going to take a very simple minded approach where we define the character variety essentially by by the ring of the regular function on them, and this ring of regular function is generated by functions which are, of course, must be invariant under the conjugation with respect to the simultaneous adjoint action. And so a typical function like that is that given an arbitrary monodromy of corresponding to an arbitrary element of the fundamental group, we consider the corresponding function M gamma, which is simply the trace of the corresponding monodromy. And so basically the ring of regular function is the ring of rational functions, if you wish, in this object. These are not independent, of course, because you can count the dimension. There are infinitely many gammas you can choose. And so there will be relations if you just take them. So they are not coordinates on this manifold, but they are functions. You could find the suitable number of independent functions that serve at least as local coordinate, but that's not the point of view we want to take. So with this in mind, Bill Goldman in the 80s in a famous paper introduced the structure, the Poisson bracket, which by now you have had time to read on the slide. And so turning the character variety into a Poisson manifold. Now, what is this Poisson bracket? It's enough since the manifold I've declared it's the ring of regular function is generated by these M gammas. It is sufficient to specify and spell out what is the Poisson bracket between any two such functions. And so if you take two loops, gamma and gamma tilde, the corresponding monodromy invariant M gamma and M gamma tilde have the corresponding Poisson bracket. So what is that? Is just the you have the let's say let's take something simple, something like that, and then so these are not based loops because after all the traces changing base point correspond to changing conjugating all matrices by a diagonal matrix, and so we can think of them as free homotopy elements. And so the Poisson bracket between gamma and maybe let me use a different color here, gamma tilde for the blue, is the sum of as many terms as there are points of intersections between the two. Of course, you choose representative so that they intersect transversally. You choose smooth representative. And this index here is just the intersection index, which is plus or minus 1 according to the orientation at the point P of the two contours gamma and gamma tilde. And this gamma P gamma tilde is the contour based at P, consisting in the concatenation of first you go around gamma, oops, right? You start at P, you go around gamma, you come back, then you go around gamma tilde, and you come back. So that's an element in a fundamental group. And you have to do that over all intersection points. This blue term here is for the Poisson bracket in the case of SLN. In general, if you have SL2, the Poisson bracket is written in a slightly different way, but it's completely equivalent because of identities between the traces. If you remove this part, and then this is the Poisson bracket for the character variety in GLN. And this piece here is essentially the effect of the Dirac constraint on the constraining the determinant to be 1. But for us, we are going to consider in the case of SLN, so this term is there. So what kind of symplectic or Poisson structure is that? Well, it's not symplectic. It has degenerate. It is degenerate, and it has Casimirs. And what are these Casimirs? Well, you can guess it already by looking at the formula itself. If you want to find a Casimir, you are looking for a contour that has good chance of not intersecting any other contour. And so, for example, if I have my contour which is contractible to one of the punctures, so any of these little gamma j's, right? This is the puncture Tj. Any of these loop which is contractible to the puncture, in the same homotopy class, you can always find a representative that does not intersect any other contour, of course, itself. And so the trace of M gamma J commutes with all other functions. So it's a Casimir. And not only that, of course, you can go around as many times as you want, and so you can take an arbitrary power. Well, also bigger than 0, but that's a little bit trivial. All right, so in other words, to put it in a different way, which is already written here, the eigenvalues of the corresponding matrices, monodromy matrices, are all Casimirs. More precisely, the symmetric functions of the eigenvalues are Casimirs. So when you have a Poisson structure, now I'm trying to be pedagogical. I'm not sure exactly for the names that I see here in the participant list is probably unnecessary, but maybe there is some also some student, right? So when you have a Poisson structure with Casimirs, then you can look at the joint level sets of the collection of all independent Casimirs, and those level sets are symplectic cleaves. So on those level sets, the Poisson bracket is non-degenerate, and when you have a non-degenerate Poisson bracket, what you can do is, if you represent it as a tensor in a local set of coordinates, you just take the inverse of that tensor. It gives you a skew-symmetric matrix that you interpret as the coefficient of a form in the same coordinate system. So if I have some coordinate system, say x, right? X mu, x nu, using not the indices above, and this, let's say the Poisson bracket is some matrix, p mu nu, which of course depend on x. If the matrix is invertible, then you can take the inverse, omega mu nu, and the corresponding two form, omega mu nu dx mu wedge dx nu. Don't ask me about the signs. I think there should be a transposition in somewhere. These two form automatically, it's closed and non-degenerate. So on the symplectic cleaves, if you write in the set of coordinates of your Poisson bracket, it will be non-degenerate, so you can make this construction. So the question is how to write in a convenient way and some kind of uniform way these two forms. This was done in the 90s in a paper of Alexeyev and Malkin. So if you fix the symplectic cleaves, and I will denote the symplectic cleave by, well, the value of the Casimir, I will use for them the values of the eigenvalues, and denote it by O sub lambda is symplectic cleave. With those particular choice of values of lambda, so there are the eigenvalues are how many? N minus 1 times n, right? Because we are in SLN. And so on that, on this symplectic cleave, you can write the two form, which I leave it to you to read off, right? It's a little bit unpleasant formula to look at, but extremely concrete. So this is a two form written in terms, written absolutely explicitly in terms of the matrix entries of the monodromy matrices of the generators. So just let's unpack a little bit this formula. So there are many pieces. There are these Ks. So what does this K is the product of the first J letters in this in the string that describes the fundamental relation in the monodromy. Except that you, for some reason, I'm just telling you what exactly is written in the paper, right? As it's written. So you consider this as one letter itself. So you would have K1 is just M1 up to KL, if L is less than N, is the product of the first L. And then starting from capital N plus 1, you get Kn plus 1 is the product of these. And Kn plus 2 is the product up to here. Okay. And then, and so on and so forth. So you have a total, as is written here, of 2G plus N. Then there are other pieces, of course. These pertain to the punctures themselves. If there are no punctures, then there wouldn't be any Casimir. The structure is symplectic, and then essentially you don't have this piece, right? And you have only the other pieces. Now, all these matrices D and P are something expressed in terms of the matrices. It's written in here below. So the lambdas are precisely the diagonal matrices of eigenvalues of the elementary monodromies around the punctures. C's are the corresponding matrix of eigenvectors. And then you do something similar for the matrix A. and the treatment is a little bit not symmetric with respect to the A and the B cycles. The A cycles are diagonalized by the matrix P2L minus 1, and the P2L is not the eigenvector matrix of BL, but it's just defined by this formula. And well, the rest, I'm just pointing out some peculiarity of this expression. So of course, this formula is a two-form. You can consider it on an arbitrary, not just on the symplectic leaf, right? It's actually, the way it's written is a form on the whole character variety, but it's a form which is degenerate. So the statement is that if you take these two forms on the character variety and then restrict it to the symplectic leaf, you can, of course, you think of the symplectic leaf O lambda as embedded into your character variety. And then you have this omega W, well, W, you have the W, let me omit this. Well, W lambda is just the pullback of to O lambda of this expression that you see here, which is defined everywhere. If you restrict, then the result is a non-degenerate two-form, so symplectic form. And the statement in this paper is that these two forms is precisely the inverse, right? Is the result of that procedure that they described in abstract terms. It's the two form corresponding to the Goldman bracket. Now, in their paper, they had some weird constants, so we had to check a little bit the proportionality constant. I think, and I hope that this is the correct proportionality constant. We checked several times, but the gist is that. Okay. All right. So now, well, this remark is maybe things. It's better to move along. Now, I want to make an extension of these degenerate symplectic form or pre-symplectic form to a symplectic form on a slightly larger space, right? So that's the extended part in the title. And the extension consists precisely in taking not just the matrices MJ by themselves, but our manifold consists on the eigenvalues and the eigenvectors, okay? So this is essentially a toric extension. It has n-1 times capital N extra variables that are essentially some scaling action on the eigenvectors. And other than that, the constraint, of course, is the same. And these is just M1 of before and Mn. Now, the same expression that you saw before can be, of course, considered in this extended manifold, but it won't be by itself symplectic. There wouldn't be any reason. And so to make it symplectic, as it turns out, you have to add this extra piece, okay? So this W that I read in here is what we want to call the extended, well, Goldman symplectic form. Now, this idea, this extension, of course, is not our idea. It comes out naturally, but it was first plotted by Lisa Jeffrey in '94, and then reprised and extended by Philip Bolch in 2007. But here our focus is mainly on the explicit formulae in terms of a set of coordinates. So now the interesting thing is that this unsightly expression that is the combination of these long formula number 4 with this addition can be expressed in a nice packaged form in terms of a flat connection on a graph, which is my next topic. So let's switch gears for just a minute, and let's consider an embedded graph on an orientable surface, C, and sigma is our oriented graph with certain vertices and edges, etc. So E is the set of edges here. And I want to define, associated to a graph, a jump matrix. The terminology is inherited from my life as a person that specializes in Riemann-Hilbert problems. So the jump matrix is just a function from the edges of the graph with values in SLN with the properties that if you reverse the edge, the jump is inverted. And if you have a vertex and you now look at the incident V, you look at all the edges that come into this vertex, then you can assume without loss of generality that they're all oriented away from the vertex, right? Because if necessary, you use this property. Then you label the edges counterclockwise starting from an arbitrary one, and V is the valence of V. And the condition that we want, this is all part of the assumptions, of course, the condition is that the product in counterclockwise order of all these matrices is the identity. Let's call this the no monodromy, local no monodromy condition. And I insist on this local no monodromy only for vertices with valence at least one. I may have just, you can allow a vertex of valence one, which then the matrix is whatever you want it to be, it doesn't matter. Okay.
Well, just to understand. So it's the right way to imagine this jump matrix as jump across the...
That's correct. So you think of
connection along the edges, it's jump across the edge.
It's a jump across, so that's the remark here. You can consider the dual graph. Okay. Let me draw it here, right? So this is the dual graph. And then you can think of this J as really connection in the usual sense, right? It parallel transport from a vector space at one vertex of the dual graph to another vertex of the dual graph.
Okay. Mm-hmm.
And so the no monodromy is just the flatness because, for example, in this picture that you see here, this little loop that is the dual face corresponding to this vertex, it's actually contractible. So you want the holonomy on this dual graph to be trivial, mm-hmm. if there are no. And in this game, the univalent vertices would be punctures. Right, so holes in the dual graph, and so there is no. In that case, you can have holonomy around them, and of course you have the handles if you are in higher genes. Okay, so now this game, right, is the following that I want to play. If I have these data, let's say a flat connection on the graph or on a dual graph, or this. Jump matrices on a graph, I can associate, for lack of better terms, we just called it the standard two form. I don't know, we can call it a presymplectic form associated with this data. So it's given sigma and J, the two form in the notation I dropped, the reference to J, it's implicit. It's, so what is that? It's a sum over all vertices. And then for each of these vertices is the sum of these pieces. Okay, so where the ingredients are more or less the same ingredients as we had above. Here is a vertex. So you take all the incident edges. Let's call J1, right, J2, J3, J, and V. The matrices counted from any of the edge you want in counterclockwise order, and then you group them in such a way that, for example, the product of the first three you call K3. Well, well, then, sorry, this would be KL inverse where DKL. Maybe yellow is not very visible.
Yeah.
Okay.
Yeah. Mm-hmm. Thanks.
Right, wedge JL inverse DJL. Okay, so this V is just to make the formula at least a little bit more correct, but I think for transparency it's just confusing. So this 1 to L is just the product of the first L. And this expression does not depend on which of the edges you start from, precisely because of the local non-monodromy condition. So each of these pieces, you can start the counting from which any edge will be the same. And then you sum over all edges. Of course, these the matrices that appear in one of the term for one of the vertices appear also in another, right? Because the same edge goes somewhere to another V tilde. And so it's not just direct sum of pieces like that. But what turns out is that, and this is essentially relatively simple to prove, that it follows from this paper of Alexei Malkin, that with the constraint in place, this object is closed. It's a closed 2 form. Whether it's degenerate or non-degenerate, that depends on the properties of your graph or the shape of the matrices, etc. But in general, it's just a pre-symplectic form. And the observation, which is relatively simple, is that this form is invariant under the standard move that you can imagine you want to subject your graph to, right? Zipping, splitting, and merging. What does that mean? It simply means, for example, that if I have a vertex and 2 edges coming out, right? And let's say this edge, they go somewhere else. Let's call J1 and J2. Then I can replace this picture. I can zip together the J1 and J2 up to a certain point and then add an extra vertex, and then they go the same way, right? So V, and this is the new edge, and provided that on this zipped thing, I put the product of the 2 in the appropriate order, which I think should be J1, J2, counterclockwise. Okay, and then of course here is J1 and here is J2. So you zip together these 2 up to a certain point, you can zip all the way together. And so splitting and merging is exactly what you expect. If I have a vertex with many legs, I can split it into, I can cut it into 2 and add an extra leg in between, right? Provided, which of course this will be J1, J2, J4, etc. So on this leg in between, because we have to satisfy the non-monodromy condition, the jump on the leg in between must be the product of these 4 with the inverse, depending on the orientation, of course, you want to put. Okay. And the merging is the reverse of this operation. So this allows you to take a graph with the given jump matrices and start deforming the graph, merging, etc., to reduce to another graph. And under this transformation, the 2 form remains the same. Okay, so it allows you to present the same form in drastically different ways, depending, because you can merge all the vertices together or split them however you like. And so now here, the first main result is this picture. Okay, this form of Alexeyev-Malkin is exactly the standard form associated to the graph that I hope you can see. Maybe I can make it bigger. Right, it's a little bit busy. So this is a piece of the surface, of course. Z0 is the base point, and these are the various, these are the punctures, T, right? And the graph has some structure, of course. For each of the handle, you see that there are these 2 loops which are more or less homotopic to each other. Sorry, they are homotopic to each other. And those are vertices. So you have to consider, imagine this whole graph. Notice that on this leg, the jump is precisely B1 inverse A1 inverse B1. And on this leg, the jump is A1 only. And now you put it into the formula, the general formula for the standard form associated with the graph, and you will get exactly the extended, what I've introduced as the extended Goldman symplectic structure, up to a factor 1/2. Okay, so just to a little bit navigate this formula. So there is, for example, this is of course the main vertex, right, where most of the magic happens, and it corresponds to this term, right, which is written in a slightly different way, but it's the same. Up to some trivial algebra is the same as the formula that I written above. And then if you look at these vertices here in green, they correspond to this and that. They give these two pieces. And let's say there are these in light blue, and they give these two terms. Now, then you can, so now you see some structure in that rather complicated formula, and now you can also try to rewrite it in a more amenable way. And the more amenable for me would be, for example, you can imagine to pull these two together, right? Zip them together. So you merge these two vertices into one, and you pull them together, and then use vertex, you pull all the way to the base point. And then you get a different graph. Of course, the form will take a different expression in terms of the jump matrices, but it's, well, you could rewrite everything in terms of this graph, right? Now, in this case, the expression would take a simpler form because you have one vertex here of valence 4G plus N, and then a bunch of little vertices of valence 4, right? And so you would have just sum J from 1 to 4 G plus N, and then trace of, you know, the formula that I was writing, 1L DJ, 1L wedge, etc., 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 etc. So, okay, and of course, if you start writing it out, it takes a completely different form. And if you didn't realize that it is associated, this is the form associated to a graph which has this kind of invariance, it would be complicated head-on to prove that they are the same form. So that's where the other part comes in. Now I want, instead of trying to pull all the vertices together, I want to kind of explode all the vertices into a simpler graph. I think I see that I was extremely ambitious. I'm just at page 11, sorry about that. So what you do is that for each of the punctures, you essentially do a triangulation with vertices at the puncture, but not exactly at the puncture. For each of the puncture, you take a proximal vertex, right? A vertex in the vicinity, and then you start triangulating with these. And so you keep this little structure that in the paper we call the cherries, because they look like cherries with a stem, right? But instead of the cherries being attached to just one vertex, they have little vertices, one for each cherry, and then you make a triangulation relative to that point. And then you have additional jumps that I've inserted. So I want to construct a new graph, and and associate jump matrices to each of the edges that you see on this graph. Even if they have different colors, all the edges carry a jump in such a way that they parameterize conveniently the monodromy representation. So how do you parameterize? Well, for example, if I want to find a monodromy, I fix the base point somewhere in one of the faces, and the corresponding monodromy would be the product of all the matrices that I cross, right? When I take my loop with appropriate power according to the intersection number. And that gives you the monodromy representation associated to this graph. Now, the only thing that remains for me to tell you is what are the matrices of the jumps relative to each of the types of edges that you can see. Now, on these black edges, the jump matrices are anti-diagonal like that, with certain parameters z. So for each edge, there are n-1 non-zero parameters zl. And for each, now this takes care of all these black lines. What about the red lines? On the red lines, you see that they are associated, each of these chicken feet are associated to one of the triangles. There is a point which we call P at the center of the triangle. You can think of, if this were SL2 and you were doing something related to the WKB, this would be the turning point. Now, then on these three edges, so for each of these triangles, you associate a certain number, specifically n-1, n-2 over 2 variables for each triangle. And they are labeled X, A, B, C, where A, B, A plus B plus C is n, and A, B, and C are greater than 1. And these three matrices, well, the construction is a bit involved. I just give some examples, right? In S2, now, of course, Leonia will be recognizing this matrix or some relative of this matrix because they were using it. There is no parameters involved for S2.
Volodya is here too.
Volodya is here too. Oh, hi, Volodya. There are 2 Volodyas at least, okay. For SL2, there is no extra parameter. For SL3, there is only 1, and then the 3 matrices are actually the same. Starting from SL4, the beauty hits the fan, let's put it this way. So because you have 3 indices, right? The sum has to be 4, 1, 1, 2, 2, 1, 1, 1, 2, 1. And then one of the matrices, well, it's written here in its full glory, and the other 2 matrices are just obtained by cyclically permuting these indices. Okay? So you cyclically permute, and the whole point of this is that this construction preserves the local no monodromic condition. So the product of these 3 matrices, the product is the identity. Okay, so the only monodromies are at the punctures, really, and of course associated to the handles. Now, I've told you what are the jump matrices on the black, on the red. What are the jump matrices here? Well, I don't really have to tell you, right? Because I just impose the no monodromic condition at this vertex, which means that the jump on the stem will be just the product of all the others. And the convenient fact here is that the jump on the stem, the product which is the product of all the others, turns out to be lower triangular. So it's particularly easy to diagonalize. The jump on this cherry is the eigenvector matrix, which is also lower triangular. And now you have also the freedom on the diagonal part of these eigenvectors. You have these extra toric variables that are essentially embody the extension of the character variety. And on this little stem inside the cherry is maybe like can write it. So here is lambda L, the jump, and here on the cherry is CL. Now I'm not sure if it's CL or CL inverse, something like that. Depends on the orientation, of course. Okay, so now if you construct now the two form associated with this graph, which is of course is more complicated because it has many more vertices. However, the computation at each vertex of these two forms, because remember these two forms is the sum of pieces, each one piece for each vertex, and they are all the same. I mean, the same structure at each vertex. So the computation is simplified, of course. For example, if all the jump coming in a vertex are triangular of the same triangularity, then basically once you sit down and do the computation, you just have to look at the diagonal part. So as if it were abelian, the computation. And so that simplifies the computation. And so precisely because at each of these vertices, the ones that I'm highlighting here, only triangular matrices are involved, one can compute easily. And here, of course, the computation is a bit of a mess, but still doable, and that's what we did. So it gives some kind of unsightly matrix of coefficients corresponding to the points inside the triangles. Now, this is a symplectic structure, meaning that it's a two form. In these coordinates that I've described, the two form that we wrote is log canonical. So what this number mean, and these xi's are just the logs. So it means that d xi a b c wedge d xi c d l, well, is the corresponding entry here. And psi, the logarithm of x, a, b, c. And the zetas are the logarithm of the z's. So there are the variables associated to the edges of the triangles. That's the way we think of it. And then these x variables that are associated to the faces of the triangles themselves, in a sense, right? Because there is one set of such variables for each. So this is not exactly what Volodya Fock and Alexander Goncharov did, right? It's an elaboration on that because they had these, these snake patterns, this sub-triangulation. It's essentially coming from there. Okay, so that allows us to compute the symplectic form, and the symplectic form turns out to be the log canonical with respect to these coordinates. So that means, right, because this complicated graph that I showed you is just a kind of resolution of the simple graph of the Alexei-Malkin graph, or the other one that I was showing. It means that these coordinates are actually log canonical for the extended symplectic structure that I've defined. Now one could ask, well, what about the Poisson structure? Okay, so can we see a little bit more of the quiver that was in the paper of Fock and Goncharov in here? Well, essentially what you have to do, you would have to take the very large matrix of coefficients in these log canonical coordinates and invert it, right, to get the Poisson brackets. So it's a little bit of a daunting exercise in combinatorics, which we verified, but I would not tell that we proved it in general. We verified for SL2 and SL3, and then we checked it with computers, etc., for SL4, SL5, etc. And so the outcome is the following: that the Poisson bracket between any, you can associate a quiver to all these variables. I will show you the quiver in a second. And then the corresponding Poisson bracket is just an integer, which is, as usual in cluster algebra, is associated to quiver in the usual way. And there is also this factor n square, which is just coming along for the right, depends on normalizations, of course. So what are, oh, by the way, right, so the statement that the Poisson structure that Fock and Goncharov has in this paper is given to, is equivalent to the Goldman bracket. I think we found in this paper of Sun in 2015, and then Misha and when we were at MSRI told us that they also have, I think, a forthcoming proof, or you already published. I'm not sure. I was checking yesterday. I didn't see. But the proof of the statement would be going through some quantum deformation, if I understand correctly from what you told us in MSRI. So what is the quiver? Sorry?
Known folklore.
Excuse me?
I would say that it is well-known folklore that it is the same. So.
Oh, it is, yes, it's a well-known folklore, right? That's, so what is the quiver of this extended version? Well, the black quiver that you can see is exactly the Fock-Goncharov quiver, right? So you see the triangle here. And then there are these extra toric variables associated with these nodes, which are attached to the normalization of the eigenvectors. And so it's depending on where the cherry sits in the triangle, right? In each triangle, you may have 1, 0 cherries, 1 cherry, or 2 or 3. Well, then the quiver looks a little bit different. So I've just drawn them here, but you don't have to stare them too long, right? So this is the most complicated situation when there are all 3 cherries inside. And these colors have a meaning. So this means that the coefficient is 1/2, and otherwise the coefficient is 1. Okay. Now for SL2, you can do things, of course, a little bit more explicitly and more geometrically transparently. And so, because you have just one variable for each of the edges of the triangulation, and one extra variable, this rho v, for each of the vertex, for each of the punctures of the, which are associated also with the vertices of the triangulations, right? Because they are proximal, the proximal end of the stem of the cherry. So in that case, the 2 form takes the simple form, the simple expression, where, well, these are the edges incident at V, oriented counterclockwise, and starting from a particular one. So if you have the vertex V, there is the cherry attached, and then there are all the other edges of the triangulation. Sorry, I should do it in black because this is the black triangulation. So here's the cherry, and then there are other edges. So these edges are only the black edges, not the red ones inside the triangles. And this cherry provides what is usually called a ciliation or cilium. So it tells you which one is the number 1. So you start counting from that. And this expression is gives this part, and then there is the one extra variable, and this extra term comes from essentially this vertex. Now, something I want to point out for the people that are a little bit more into this kind of games is that this part, so I would put my thumb on it, but you wouldn't see the thumb, right? So the part which is not crossed out, okay, or let's put it this way, let's be active. This part in the box is not invariant under the choice of ciliation. So if I move the cherry somewhere else, the expression would be different. But the total is invariant under the choice of ciliation. And in particular, if I change, however, unless you are, sorry, on the symplectic cleave. So you impose that the eigenvalues are constant. The eigenvalues of the monodromy turned out to be just the sum. So V is just the product of the ZE for the E incident at V, where this is V, plus or minus, which is not so important. So if you impose this, that you are on a symplectic cleave, then this expression would be invariant, and this is 0 because, as you can see here, is the sum, right? This sum here is exactly the logarithmic derivative of the eigenvalue, and that would be 0. So the Poisson's tensor of corresponding to this extended symplectic form is written here. I will not spell it entirely, the symbols. If you want to see it, is in the paper, right? And in this case, the quiver is this form. So this is the quiver, the Fock-Goncharov quiver, and this is the quiver with the added toric variables. In the case, there are all the 3 cherries inside the same triangle. Otherwise, you have to cut out one of the 1, 2, or 3 of these corresponding vertices. Now, this story, of course, is familiar for people in the business, and it tries to answer the question: what happens? I think I probably should speed up or cut out. What happens if you change the triangulation? And so, of course, you are expecting to see the Rogers dilogarithm pop out, but I want just to give maybe a perspective on what is the Rogers dilogarithm here. So you have a symplectic form associated to the graph, right? And then, because it's symplectic, you can construct the symplectic potential. So it's a 1,4, specifically this symplectic potential. It implies a choice of polarization, right? And the way I'm writing it. So it's the one form such that its differential gives the symplectic form. But this choice, of course, is not unique. They differ by the differential of a function. And now the question that you ask is, what happens to this symplectic potential if you change the triangulation? Or in other words, for example, by an elementary move consisting in flipping a, so if you have, well, I have the picture on the next slide, sorry. Okay, so here are 4 vertices and 2 triangles, and these are the little cherries. And now I'm going to change this diagonal to the other diagonal. And the question is, what happens? Of course, in doing so, I want to insist that the monodromy representation remains the same. And for that to happen, well, the corresponding edge coordinates have to transform in some way. Now, because we are dealing with SL2 and not PSL2, there are some unsightly signs, right, that appear here. If we were considering in SL2, the relevant variables would be the squares of these z's, and then you wouldn't have square roots and you wouldn't have signs in the game. So if you do that and then compare the 2 symplectic potentials for the corresponding 2 symplectic form, which is, of course, the symplectic forms remain the same because flipping an edge corresponds just to a contraction and an expansion of edges. So by the little lemma that we proved, the 2 form is invariant. Then you will get that the 2 corresponding symplectic potential, they differ by the differential of the symplectic, the differential of the Rogers dilogarithm that you can see here. Of course, this was exploited in many different, with many perspectives by Tomoki Nakanishi and Misha Gekman Nakanishi and Ruppel in 17. And this kappa here is just z square, and z is the edge coordinate of the edge being flipped. So that would be this one. Sorry, somebody's entering. I'm gesturing not to enter. That's what happens when you live with your parents. Okay, so temporarily. Now, this allows us to define the line bundles. I want to think of this dilogarithm as transition function of a line bundle over, well, to be precise, here it would be really over the quotient by the character variety, the SL2. Here I'm using now SL2R with respect to the mapping class group, so the modular space of punctured Riemann surfaces. And a way of interpreting all of the above, I'm sorry, I'm running out of time, is to interpret the Rogers logarithm as the transition function between two charts related by an elementary flip of the diagonal. Now, to make it in such a way that the co-cycle condition is preserved, you have to negotiate with the identities of the Rogers logarithm, which are these two famous identities, the Euler identity and the pentagon identity. And because of these strange numbers here, you have to make sure that to multiply by the appropriate factors so that they become multiple integers of 2 pi I. So that's the reason of this factor here. In principle, as we discussed with Volodya and Mr. Rai, by choosing different co-cycle representative, you may actually knock down this 12 to a smaller number. So what I'm defining here are transition functions of a line bundle, which is actually the power, an integer power of a line bundle. And this line bundle is actually the line bundle whose curvature form is the Weil-Petersson form. Now, I think I'm trying to say too much in too little time by now, so I'll just leave the slides at the end and I will stop here. Okay. Thank you very much.
Thank you, Marco. Any questions?
Can I ask a question? Maybe stupid. Just to the last dilogarithm line bundle, is it possible to think about it like about a kind of determinantal bundle and then to use a geometric quantization procedure?
Well, okay, so not sure about the determinant line bundle, but you could try to do geometric quantization, of course, and I think maybe Lonia here has something more to say, but in order to do that, you have to be sure that the 2 form is integer class, right? So it has to satisfy an integrality condition, and that essentially is the story that I'm trying to communicate. Here is the choice of this integer here. So by this one, I presume it should be quantizable, and I think actually it was quantized, right? Maybe not in these precise terms as the way I'm expressing, but I believe that Fock and Goncharov did actually have this quantum version in their paper. Although I have to admit, to confess that I had a hard time reading it, with apologies.
Okay, thank you.
More questions?
There's
question.
Right, please.
Okay, so instead, if you do the formation quantization of the character variety, do you know how to see the algorithm there?
sorry, the what?
a deformation quantization, which let's say also depends on your triangulation?
No, I didn't do it. So it would be the starting point. But again, I think these questions would probably be turned to Liania or Volodya.
Okay.
Yeah. We didn't do anything, any quantization or deformation quantization in this.
Other questions? Well, if not, let's thank Marco for great talk, and please send me your slides later.
Yeah, I will send you, I will clean up a little bit of the mess and send it to you.
Yeah. Thanks again.
Okay, thank you. Thank you.
Yeah.
It was a pleasure.
Yeah. Thanks, everybody. Yeah.
So we just...
I will kind of...
Что занятие сейчас?
And yeah, just a reminder that next week we have Chris Fraser. Okay, thanks.
Yes, thank you, Marco. Thank you.
Thanks. Thank you. See you next week. Bye.
Yeah.